the logic of the compound statement. So the logic form and logically equivalent. So maybe you can have a look at here. This guy is not a mathematician, but this guy is a philosopher. And logic, right, is a science that is developed by, you can say, mathematician or by philosopher. And actually, he writes a book called Logic. And then I got this. I haven't read that book. So maybe you have a look at this passage, okay? So an argument is just a sentence, okay? Whether that it has a truth value. So what does mean by a truth value? So let's say I'm a boy is an argument. But if I say let's say are you hungry? Okay. This is not a argument. It does not have it is not true or false. But let's say another argument, okay? Do the homework. And this is also not a argument. An argument is a sentence which can be true or false. The assertion of the end of the sequence is called a conclusion, okay? The preceding statement is called the premises. So conclusion and the premises can also have the truth value. Okay. Then let's go on to have a look at this statement. So if the bell rings or the flag drops, so these two are premises. So either then the race is over. Then this one is the main body, the argument. Okay. So if the race is not over, then the bell hasn't run or the flag hasn't dropped. So actually, do you notice that what is the difference between these two sentences?
It's sort of just reversing the conclusion and the premises. Is it? It's just reversing it, sort of. I guess.
Actually, we will show that these two statements are logically equivalent. I'll give you another example here. If x equals 2 or x equals -2, then x is squared equal 4. If x is squared not equal to 4, then x not equal to 2 and x not equal to -2. Actually, you can see that the argument 1 and argument 2 are quite similar. They have the same structure.
Yeah.
Yeah. By doing the logical analysis, it doesn't matter whether what is the content of the sentence. We just look at the structure. So they have these two arguments, the same structure. We say that they have the same structure like this one. Okay. And then for logical, we are analyze this kind of structure in this chapter. So you can skip this one. So for compound statement, actually we have talked about it a little bit. So there are a few things. Let's say you need to learn about the symbols. For if you have taken the RGCSE physics about the topic about logic gates, you should have encountered more symbols already. So this one, it means not P, okay? You look at here. Then this one means and this one means or. That's it. That's it. Okay. For some kind of compound statement, maybe compound square, they have more than one operation, like this one. So if we interpret this one, of course, we know we do the operation inside the bracket first. that means P and Q first, and then or R. The order of the operation may matters. So that means this one and this one may not are not equivalent to each other. So you need to look carefully at the bracket. But we have the order of operation. So let's say the order of the operation we starting from the negation mark, and then so we first do this one first. So and then we do the bracket, and then we do this one or this one. So what I mean if you look at this sentence these two are equivalent because we do the negation first. So whether you put the bracket in the negation P it doesn't matter. They will give you the same result. Any question here? No?
No.
But this one are not the same. This one are not the same. Now, although we do the negation first, but we do the negation of the whole object, whole P and Q. But this one we do the negation on P only. That means not P and Q. But this one is not P and Q.
Like we first find out P and Q and not that.
Yeah, not only on
like
P.
yeah, like you can use like Venn diagrams.
Yeah. Okay, if no question, then let's go on. You may need to also know how to convert the daily language to the symbol. P but Q actually mean N. Neither P nor Q actually mean not P and not Q. So and then maybe you can have a look at this example.
Wait, sir, are these both the same? You have P and minus Q. Are they the same as this?
P or Q.
Huh? Are they the same?
No.
No.
We will learn how to show that we will learn some of the identities later. Okay, this one I think not difficult. Not hot, that means actually, but means and sunny. Okay? Neither hot nor sunny. That means it's not hot and not sunny. Not hot and not sunny. Simple. Okay. And then truth value, they're true, okay, either true or false. And sometimes we use 1 represent true and 0 represent false. Just like in physics. If you still remember, we use the 1 to represent true and then F represent false. And then let's have a look at the truth table for P and Q. If this is a P and Q, so for P and Q, it is true only if both of them are true. Okay? Either one of them is false, then the P and Q is false. Okay. I think it's not difficult, is it? If not difficult, then let's go on. For P or Q, if either one of them is true, then the statement is true. If if both of them are false, then it is false. That's it. In C purpose, they use this kind of notation in the program. Okay, because you can't type this one in So you in the programming language, they use this one represent and use this one represent or. Okay. So and then let's go on to have a look at some more truth value table. So let's say this one. Can you see this is so complicated? So this has
Yeah.
Q and then negation P and Q. So what did we do here? Actually, we want to know if P is true or let's say if P is true, Q is true, what is the truth value of the whole statement? So what we do, we draw a, if we want to know about all the possible outcomes, so we draw the truth table like this one. So there are only 4 possible outcomes here, only four possible outcomes. So either P is true or false, either Q is true or false. So in total, there are 4 possible outcomes here for P and Q. So the input is, there are only 4 possible inputs, and then there are only 4 possible outputs. And then we look at it one by one. So how can we look at this one by one? First of all, we look at this one. This is the first one. Then the second one is this one. And then the third one here, including the negation. And then we do the final one, the fourth one. That means the whole statement. Do the 1 and 3, okay? Here is 1 and 3. Here is only 1, here is 2, and this is 3. So we do it one by one. So maybe you can have a look at the statement or. If this is P or Q, that means either of it is true, then the statement is true. So true, 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 false. P and Q is if either one of them is false, then it is false. So it's true, false, false, false. Then negation of it, negation of P and Q, so you just true become false and then false become true. Okay.
Okay, so just a reminder, negation is just not, right?
Yeah, negation is not. Okay. Yeah. Negation is not. Why I say negation? Negation because I think the philosopher or I'm not sure who used this term. So you just say not, okay? So not in Q, and then so we look at these two, okay? Oh, if true and false, they give you false. True and true give you true. True and true give you true. False and false give you false. That's it. So we have a we have a table like this one, okay? And then if no question, and then you can have a look at this one. Because there are 3 variables, so either P, Q, or R can be true or false. So in total, there are 2 times 2 times 2. That means 8 possible inputs. So and then there are 8 possible outputs. So maybe you take 1 minute to have a look at this table. Now, although you may not encounter this kind of question in the exam or so in a competition or in exam, but this kind of logical training is very essential for programmer. Finish? Any question here? No? Yes, no?
No question.
If no question, then maybe let's go forward, okay? So this is very important. If two statement forms are logical equivalent, they have the same truth value for each possible situation or input or output. That means they have the same output if for all possible inputs. So we will have a set of first of all, these two are equivalent, okay? Then this is not difficult to understand. Not P is equal to P, okay? So and then this one, the one that Harsh asked me just 10 minutes before. So we can use a truth table to show that these two are actually not equivalent to each other. Maybe we can have a look at this table. Any question?
No.
But we can show that this one is equivalent to, or equivalent, we use this symbol. This one is equivalent to not P or not Q. So let's do not P and not Q. Not P or not Q. You can look at these two column. For not P and not Q, so this one is false or false, and give you false. False and true give you true. True or false give you true. True or true give you true.
True or false?
True or false give you true.
Oh, yeah.
Okay. So right now you can see that this row, this column, this column has the same truth value as in this column. So what does it mean? It means that these two statements are logically equivalent. Okay. Okay. So
Okay.
Okay.
this may be the first one you may need to remember, but actually, there are few of them. This one is equivalent to negation P or negation Q, and then negation or not P or Q equivalent to not P and not Q. So you can check this one by yourself after the lesson. But not this one. You can check this one by yourself after the lesson. So let's have the De Morgan's law. If you still remember, you have this law in where? In set theorem. Do you still remember? Do you know this one? Probability A union B equal to probability A plus probability B minus probability A intercept B. Do you know this one? Hello?
Nope.
Yes.
You learn it in form, which form? Hello?
I learned Form 5.
Hmm?
Yeah, they actually taught us in Form 5. Maybe they taught us in Form 4, but I don't remember.
So don't worry a lot, okay? We'll learn it. Learn this law in set theorem later on. Actually, it's very easy if you draw the Venn diagram. You can put this one very easily. So this is just what we what I teach told you just 1 minute before, okay? Okay, these two. You can show these two are equivalent, logically equivalent. Okay. If no question now, and I'm not doing this question, okay? You can read it by yourself. So and then let's have a look at here. This one, tautology, I don't know how to say. This statement is a statement that is always true. So the easiest statement that is always true is the true statement, okay? So let's say, what statement is always true? Let's say,
The sun always rises in the east.
let's say Harsh is boy, okay? So it's always true, okay? So this is a true statement. And then a contradiction is a statement that is always false. So what kind of statement is always false? Harsh is a boy, is a girl. So this is a statement that is always false, okay? Like this one. So there's some kind of tautology. Let's have a look at this one. So if P or not P, then this is always true. P and not P, this is always false. So what does it mean? If you always see this kind of statement, if you see this kind of statement, and then you can replace this one by a small t, a small f. Represent that is always true or always false. So let's have a look here. I think they may use C or F to represent the contradiction or a false statement. Okay, like this one. So right now we have learned about this everything here. So let me capture a screen and then send in a group. So of course that's not the end of the story. So we still have a lot to learn about the logic. To simplify the statement, okay, let's have a look here. If we want to show that this one equal this one, now of course what we can do, we can draw a truth table to show it. Because if we want to show that these two statements are logical equivalent, we can use a truth table to show it. But except using a truth table, we can use a mathematical. You may have a look here. Do you know what it's doing in the first step? It replaces this one by this one.
Yeah.
So what it do is negation, negation square and circle equivalent to negation square or negation circle. Okay. And then negation P that gives you P or negation Q. And then what it did in the next step is using the distributive law. Have you learned about the distributive law? Did we?
No.
Oh, this one. You haven't learned about it? I can't see in the, yeah.
that actually does work, you have to say pick a suitable agent. He's not the master.
But maybe you consider these two laws are the you just memorize these two laws, okay? The associative law and then the distributive law. Now you can prove it by drawing the truth table. Maybe this is a homework for you, okay? To demonstrate these four laws that are equivalent to each other. The associative law is easy. Yeah. And then, so this is homework for you, okay? So they use the distributive law. So let me write down the distributive law for this one. So if it is a or if this A or B and C, this is equivalent to A and B or A and C. Oh, sorry. It is equivalent to A or B and A or C. And then you use this law. Then this one will give you a contradiction. If P or contradiction, it will give you P. I think you may need to spend some time on doing this kind of question to familiar with yourself.
Sir, why does P or contradiction give you P?
The contradiction is a false statement. So that means P or false statement. If this is an or operation, it doesn't matter whether this one is a false or not. So let's say P is true or P is false. This is always a false statement. So if P is true and if P is true and then the P or false will give you true. If P is false and then the final output is also false. So it doesn't matter. So it is equivalent to P. Should I draw the truth table again? What I mean is this one. P or F. So or means either one is true and then it gives you a true statement. Okay. You can see this one actually is equivalent to this one. So they are logical equivalent to each other.
Okay.
No question? If no question, now you read it by yourself, okay, and then you can do some question by yourself. For choosing the question, you can just choose the question with only this kind of symbols. Okay. Okay, the next one is the most difficult one. It's about the conditional statement. For conditional statement, that means if and then P. If this one means if P then Q. Then the truth table is like this one. Now, I understand that it may be difficult to understand these two actually. This one. Let's say in daily language, okay? I think the first two is not difficult to understand. But I should have given you an example last time. So let's say if it rains, then the floor is wet. So this I give you this example last time. So it rains is a statement P. Floor is wet is a statement Q. So let's say if it really rains, okay, then the floor is wet. So that means this is logically valid. That is correct, okay, logically correct. So then if it rains, but the floor does not wet, it's not wet, then it is logically false, okay? But let's say if it does not rain, that means this statement is false. Then the floor is wet. This is still logically correct. Do you remember what is the explanation? Hello, hello. Hello, hello.
Hello.
Can you explain why this is still logically correct?
Because the floor can be wet for other reasons too.
Yeah, so let's say the floor is wet because you pour some water on the floor. So there's different causes that cause the floor is wet, okay? It need not to be due to the rain. So it can be other reasons. So this can still be logically correct. So this is a true. And then this, if these two are false, and then this is true, I think. Okay. So the most difficult part for you is to remember this one. If no question, then let's go on now. Now, actually, this one is quite interesting because there's an equivalent statement for this one. Or yeah, this one. So if P then Q, it is equivalent to not P or Q. So maybe you can have a look at the truth table. So let's draw a truth table together. PQ, okay. P then Q, and do the negation P, and then do the negation P or Q. So all the possible outcome possible inputs true true false false true and true false false. So maybe can you spend some time to finish the truth table? Now you can write on the screen, okay? Okay, I think it's not too difficult to show that these two are logical equivalent, but it may be difficult to remember actually. So you just consider this is an identity that you may need to use it very often. Okay, so we have shown that these two statements are equivalent to each other. So let's go on to have a look at some other statements. Okay, let's say this one. We want to show that this is they are equivalent to each other. So one method to do it is draw the truth table. This is always a easier method because you don't need to think about the steps how to prove it mathematically like this one. But let me show you in a few minutes, okay? So show you how to show that these two statements are equivalent to each other mathematically. Let me see which one. Where is it? Where is it? Oh, yeah, okay. So which one do you think is easier to start with? The left-hand side or right-hand side? No idea.
I think left side is easier.
Left side is simpler. So we start from right-hand side, okay? Because right-hand side is more complicated. So I would like to always to starting with a more complicated one first. So this statement is equivalent to, so we can apply the identity that we have talked about, okay? This one. Negation P or Q. No, P or R. And negation Q or R. So what's the step next one is using the distributive law. So let's say it's A or B and C let me so we can cheat. Okay, we can cheat using this table. So then we use the now you can consider this one as a whole object. So this one and negation Q or R. So this one and negation Q or R. So what you can do is using which one? This one, okay? You can use the distributive law. So it's wow, it seems so complicated. Or actually, they can actually you can use this one. So you can see or no, they are not the same object. Yeah, they are the same object.
We can take the R out as the common.
Yeah. So the R is a common from in these two statements. Okay. Maybe let me rewrite this one. R or negation Q. Okay. So and then you can use this one. P is the R. Okay. That means R or then there is the negation P and negation Q. Okay. Any question here? No.
No.
And then for if we take out the negation from the brackets, that will give you negation P or Q. Okay. And then we use what we have learned about if P then Q, that means negation P or Q. Okay. So right now we have negation, sorry, P or Q implies R.
Yeah.
So then we can show that these two statements are equivalent to each other using the laws, okay, instead of drawing the truth table.
So the laws are, you remember them just so that it's quicker instead of drawing the table?
Yeah, of course, it's always quicker for than drawing a table.
Okay,
but
okay.
if you don't want to think about the laws, drawing a table is definitely a method for you, okay? It may be an easy method if you forget the law or you're very bad at the proving in mathematics. Okay, then you can have a cap screen, okay? Or let me cap the screen. If no question, then let's go on, okay? Let's have a look. So I think we almost finished this chapter already. So So just some layman term, okay? Converse and inverse. Converse, that means you okay, like this one. The inverse is this one. But actually, it may not be quite useful. Now, only if P only if Q, that means if P then Q. So you need to learn this kind of language. Then for biconditional, biconditional actually is quite similar to equivalent to equivalent. So if P and Q have the same truth value, then this statement is true. Okay? If they have different truth value, then this statement is false. But it may not be quite useful. I think we have finished talking about this session already. Let me see. You may learn this word, okay? Sufficient condition and necessary condition is so important in mathematics about these terms. And then I think we have finished this session already. Yeah, yes. Is it? Oh no, not yet. Valid and invalid arguments. We can skip this one, okay? Because a little bit too much here. But I think it's good for you to have read this one. So this is very important in philosophy actually. So you may have a look at this chapter also, okay? If you want to study the computer science in university, so you.
Wait, sir, is there any way we can use proof by induction in this?
Induction.
Like for like in the above, like we did proving, right? Yeah, could we possibly use proof by induction?
No. What do you mean by proof by induction?
Like let n equal to okay. Oh yeah, it doesn't work in this case. It only works with numbers, right?
If you want to learn more logic, you may look at some of the philosophy books. It is quite interesting. So just like whether the logic is created by God or not, this is a good question already. So let's say if without God, is there any logic? Or without human, is there any logic? So like this one. So I think this one is actually this is as around 2,000 years old, more than 2,000 years old. So even in the Aristotle, the age of Aristotle, there is he already writes a book about the logic already, talking about this kind of statement. But you may have a look here, okay, later on. So this is an application for the logic gate. So if you study, if you will study RGCSE physics, okay, you may have a look, okay. You must have a look, okay. It's just you need to learn this one, okay, in physics. This kind of symbol in physics. Okay. So actually the same, actually quite similar to what we have learned. So then we finished this chapter already, okay? Yeah. Okay. Number system and circuit addition. Then so let's have a look if you know how to do this one.
Yeah, easy.
Because there's some question about this one. the binary numbers. Oh, so express these decimal integers in binary notation. Do you know how to do it?
Yes.
When did you learn it?
I learned it from my dad.
I think we learned it in Form 2 or 3.
Yeah, so maybe we can skip it.
I think Form 3, yeah. Yeah, everyone already knows it.
I think, yeah. How about the addition or the subtraction? Not really.
Oh, wait, no. I'm thinking about ICT. No, we didn't learn it in math class.
Oh, do you take ICT?
I used to. It's an HKGSC subject only. So next year I'm gonna take self-study computer science only.
Oh, yeah.
We didn't learn too much about the addition and subtraction yet.
Yeah. So maybe I do an example for you, okay? So let's 1011, okay? 101. So what we can do that is we don't we just consider this as decimal numbers. We don't what we do that is you know from primary school, okay, the value should be 1112, okay? 112. But if this is a binary number, you know that there's nothing, it doesn't have a number 2. So what we will do that is add 1 to the before, and then this one becomes 0. But if you add 1 in the previous number, it's become 2 here. So you do the same step, okay? The final answer should be 10000. Easy.
Oh, okay.
Yeah.
So like this one, okay? So if you consider this as decimal number, so give you 2012. But you know that it doesn't have a 2 in the decimal binary number. So it should be 10, and then 2 plus 1 plus 1, okay? Then that is the final answer.
Oh, okay, that's cool.
So that's easy. But for subtraction, you do something similar actually, but it may be a little bit difficult. So let's say if 10 minus, 10 minus 1 give you 1, okay? 10 minus 1 give you 1. Actually, 10 means 2 actually, okay? You can consider
Yeah.
it. So this one you can consider this is 2, and then you can consider subtraction of 2100 minus 1101, and you can consider minus this one first and then minus 1 afterwards. So if this one minus 1100, then give you 1000, and then you minus 1 again, so you give you 111. Yeah, the final answer should be 1.
Okay.
So wait, what did you minus 1?
Because the original number was 1101. So then to make it faster.
Oh, okay.
Yeah. Or you can have a look at these, okay? So later on. And then, but for the addition or the subtraction of a has a decimal number, it's so complicated maybe already. Yeah,
but then we can like change them into base 10, and then we can add and then change them back into.
Yeah.
But that's way more simple.
So we finished chapter 2 already lah. So we'll next time then we'll have a look at a little bit about chapter 3, but we will not go in deep about the chapter 3. So I'll just tell you some simple laws about the chapter 3, and then we'll go on to have a look at the counting techniques about the chapter. Let me see which one. We use another book for number theory, and then we go on to have a look at the set theorem. Okay, we go on to have a look at the set theorem, and then go on to have a look at counting and probability. Yeah, we may still need to spend 4 more lessons on the mathematics part. Yeah, so maybe you really need to watch those videos for programming. Okay, you can ask me questions about the programming, the C++. maybe I'll try to make some video also, but it's better the YouTuber teach better than me, okay? So you can have a look at the video by yourself. So for later lesson on Monday, okay, can we change it to on Tuesday? On Tuesdays.
Yeah, it's okay.
So I'll send a message in the group, okay? So and then see you on
next Tuesday then.
Tuesday, okay?
All right. Bye-bye.
Bye-bye. No question. Bye-bye. Bye-bye.
Bye-bye. Have a good weekend.
Bye, sir.
Bye.
Bye, sir.
Bye. Bye-bye.